Hello guys, today we'll be looking at taking thickness measurements at high temperature. Oftentimes, this is one area that technicians overlook, and they feel that the temperature does not have any effect on the thickness of the material being measured. We're going to look at how temperature affects the thickness and what you can do to compensate for that temperature change. So let's get to it. So we'll look at how taking a thickness measurement at high temperature. By design, most of your probes will normally operate between 20 degrees Celsius to 50 degrees Celsius, which is your normal atmospheric or room temperature, depending on where you are. Now, when you are taking thickness for hot surface, let's say you have a boiler. This is a boiler, or maybe a heat exchanger, where you on the shear side you have very high temperature. You can even have a boiler in some cases when they are not insulated, you can have up to 500 degrees Celsius. In some heat exchanger, you can also have temperatures that are even as high as 200 degrees Celsius. And you want to take thickness on those areas. In principle, the velocity of the sound wave in a material will reduce as the temperature is increasing. As a matter of fact, if you have for every 55 degrees Celsius, which is 100 Fahrenheit of temperature change, the velocity will reduce by 1%. What this means is that if I have my normal velocity of sound at 5920, by the time I increase the temperature by 100 degrees centigrade, the velocity would have reduced to 5820. And by the time you take your thickness measurement, you will be having about 1.7% differences in the thickness. So now imagine taking thickness for a surface that is about 500 degrees Celsius. You can imagine what changes would have become as you take the thickness. Normally, when there is increase in temperature, the variations you will see them in your thickness. But if you are using your regular probe, you will not notice these changes happening because you did not take that into cognizance and there was no compensation for that. When you are doing your final calculations on maybe your corrosion rates or whatever the analysis you are doing with the results of the thickness measurement, it is going to affect the final result. So how do we resolve that? There are a couple of ways to go about it. The first method is you are going to use what we call your high temperature probe and couplet. The second method is you use what we call your delay line probe. And the third one, which is the one that you can easily do, is what we call your temperature compensation. So let's just go through the three of them to get an idea of how you go about that. So for the first one, we have our high temperature probe slash the couplet. In this case, if you have a very hot surface and you want to perform thickness measurement, you look for a probe that is able to withstand high temperature. By design, if this is your typical probe, so this is your probe housing, normally you will have an external protection for the probe, which is called your probe shoe. These parts can wear off easily, and when the temperature becomes very high, can also melt. And of course, the temperature change, if I have a body that I'm taking a thickness, let's say this probe is on the surface, the effect of high temperature on this surface that I'm gauging will be transmitted. Because of the hot surface, it will affect this coupler and it can melt off. Also, the changes in the temperature as the velocity is changing in the material will also affect your reading. So when you use high temperature probe, this shoe is usually made of a high temperature material that is able to withstand high temperature. In your couplant, when you use your typical couplant that you use for maybe 20 to 50 degrees Celsius, it's going to evaporate at very high temperature. In some cases, the high temperature will affect the coupling effect. So to compensate for this, you use high temperature couplant, which does not easily evaporate. In this case, you are trying to, should I say, mechanically compensate for the temperature change. In the second case, you use what we call a delay line probe. By design, a delay line probe, so you have your normal probe with your transducer inside. Instead of having this flat shoe, you are going to have a very thick probe shoe. So let's say the probe, this material normally for typical available delay line probe is made of perspex. So you have very thick perspex here. Sometimes it can be as thick as 50 mm. So when you put it on the material, whatever changes that are supposed to affect this probe from the hot surface is compensated because of the thickness of this delay line probe. And when you are doing your calibration, you have to compensate for this change in the delay line. The third method, which is easily available to everybody by design based on the thickness measurement device you are using, whether you are using your typical 38, 39 DL or you are using Sinus or your Olympus unit. They have features in the machine that will enable you to do what we call temperature compensation. So in that case, you can use your typical probe that you use at this temperature and you compensate for whatever temperature change that occurs. But in case where you are going to have very high temperature that is going to affect your probe, you still have to change your probe to a high temperature probe while also performing your temperature compensation. So practically look at it, how to do temperature compensation and to get the accurate reading due to temperature change. We'll now illustrate this temperature compensation concept. I'm going to use two units, 39DL and Sonates D10. If you look at this, your probe, this is the shoe that we're talking about. If the temperature becomes very high, this is a perspex glass, not designed for very high temperature, it can melt. And then the material you are taking, the thickness also, it has the ability to burn off this probe shoe. So for very high temperature, for say 500, 200 degrees Celsius, this probe will not be used. You need to use a high temperature probe. And of course, you are going to add your high temperature couplant. But for very moderate temperature between 50 to 150 degrees Celsius, you can still use this probe while you do your temperature compensation. These two machines have been designed for temperature compensation. We'll start with the 38DL. If you look at the menu, the setup menu, if you go down, you will see this temperature comp is always there. If you see this temperature comp, you will see this arrow where you see temperature comp enable. That's temperature compensation enable. Of course, there are other things like your degree in units, your degree units, your calibration temperature, your temperature coefficient, and your current temperature. If I open this first menu, all these things will be taken care of. Now, I want you to also have this at the back of your mind. Your material you are calibrating with your calibration block, it's at room temperature. The material you are testing is at a different temperature. So definitely there will be a temperature change which will be reflected in what we call your temperature coefficient. In this case, the machine automatically does the calculation. So if I go to temperature compensation enable, it will give me a menu. From this menu now, you can see that temperature compensation is off. So if you want to do high temperature measurement, you need to go and turn it on. So now it's on. Now, there is a term, a statement that is here. You really need to take this into consideration. So temperature compensation only apply to dual probe. So if you are using a single element probe, this will not support it. Now, if you look at this probe I'm holding here, this is a dual probe. You can see the two elements inside separated by this partition. So which means this probe is suited for high temperature. This also is a double element probe which you can also use for that purpose. But if you have a single element, do not use it. How do you verify? You see the partition in between that separates the probe. So if you look at this, you have this partition. When you have ensured that your high temperature probe is in use, your temperature is in Fahrenheit here. You can convert to degrees Celsius. Look at the option, so it's in Celsius. Now, your calibration temperature, this is the temperature of your calibration block, which is usually your room temperature. So you put that, and your current temperature, which is the temperature of the material you are going to measure. So if it's at 200 degrees Celsius, you come this place and then and put your 200 degree or whatever the temperature. Your temperature coefficient, that you can calculate on your own or automatically. The machine does that for you. Immediately you enter this value and you go to your measurements, and of course you are going to do your normal calibration, your setup and all that. So what this covers is just for your temperature compensation, but that does not take out the fact that you have to do your calibration and all for other things. For your sonar test, if you go to your menu and you go to your measurement menu, you always see this T-comp. T-comp here is temperature compensation. As it is here now, temperature compensation mode is off. So if you want to compensate for temperature, you turn it on. Immediately you turn it on, you can now put your calibration temperature, your material temperature, and your temperature coefficient. Every material has its temperature coefficient, so always verify the temperature coefficient of the material, impute it, and you are good to go. So what the unit does after putting these values, the equipment will automatically do the compensation for your temperature change, and if there are variations in thickness which is due to high temperature, the machine automatically calculates it and gives you the correct reading. It is very key that you do this. If not, you will be having your readings that have out of your expected thickness. To conclude on this, how do you go about if you are going to measure high temperature space? How do you go about it? Typically, for all inspection, you are supposed to ask for information concerning the material you are testing for. If you are giving maybe the spec of all the design documents or the drawings, the construction drawings of the vessel, you should go to the temperature column and see the working temperature of that particular unit. With that, you should be able to determine if it is a high temperature thickness you are going to take or if it is a room temperature. In other case, the API inspector should tell the TM technician it is a high temperature job, so that the technician is able to prepare getting the high temperature couplant or getting high temperature probe. Or also the TM technician for probes like this. Now, this is a typical sonar test probe. If you go to their website, you will see the information concerning this probe on their catalog. The optimal working temperature and the range of temperature where this probe can function properly will be given. Do not assume that this probe rather will work at a specific temperature. Do not even take my word for it when I said 20 or 20 to 150. Go to the Sonatest website, check the probe specification. It will give you the maximum temperature range. If the temperature does not work for the probe that you are using, please look for the appropriate probe. If you take these precautions, I believe at the end of the day, your results will come out well. Thank you.